Please help us by visiting and subscribing to our YouTube channel, and don't forget to click like and share. Extraterrestrial weather patterns, insights into outer space conditions. Outer space, though often considered a vacuum, is not devoid of weather patterns and environmental phenomena. Understanding these extraterrestrial weather patterns is crucial for space exploration, satellite communication, and even the protection of astronauts. In this comprehensive exploration, we'll delve into a range of fascinating facts about outer space weather patterns. Solar wind. The solar wind is a constant flow of charged particles, mainly electrons and protons, emitted by the sun. This solar breeze impacts the Earth's magnetic field and can lead to geomagnetic storms. Solar flares. These are sudden, intense bursts of energy and radiation from the sun's surface. Solar flares can disrupt satellite communication and even pose risks to astronauts in space. Auroras. The interaction of solar wind with the Earth's magnetosphere causes the breathtaking northern and southern lights, or auroras. These mesmerizing displays are a result of charged particles colliding with gases in the Earth's atmosphere. Cosmic rays. High-energy particles from distant supernova and other celestial events bombard our solar system. These cosmic rays can impact electronics on spacecraft and potentially pose health risks to astronauts. Magnetospheric storms. These storms, driven by solar wind, can disrupt power grids, GPS systems, and communication networks on Earth. Space weather forecasting. Scientists use a network of satellites and ground-based observatories to monitor space weather conditions, providing crucial data for predicting solar storms. The solar cycle. The sun's activity follows an approximately 11-year cycle, with periods of high and low solar activity. Understanding this cycle is essential for space weather forecasting. Electromagnetic storms. These storms can interfere with radio signals, making it challenging for astronauts and spacecraft to communicate with Earth. Solar minimum. This is the period of the solar cycle with the lowest solar activity. During solar minimum, space weather events are less frequent but not absent. Solar maximum. The opposite of solar minimum. This is when the sun is most active, with an increased number of sunspots, solar flares, and other space weather events. Space radiation. Astronauts are exposed to higher levels of radiation in space than on Earth, which can increase their risk of cancer and other health issues. Cosmic dust. Space is not entirely empty. It contains tiny particles of cosmic dust that can pose risks to spacecraft and their equipment. Solar eruptions. Prominences and solar flares can eject massive amounts of solar material into space, potentially impacting satellites and the Earth. Magnetopause. This boundary separates the Earth's magnetic field from the solar wind. Understanding its dynamics is crucial for predicting space weather events. Van Allen belts. These are radiation belts surrounding Earth, trapped by the planet's magnetic field. They can impact satellite operations and astronaut safety. Ionospheric disturbances. Space weather can affect the ionosphere, which plays a vital role in radio wave propagation and navigation systems like GPS. Coronal mass ejections (CMEs). These massive eruptions of solar material can cause geomagnetic storms on Earth, disrupting power grids and communication systems. Spacecraft shielding. To protect astronauts and equipment from space weather, spacecraft are equipped with shielding materials to absorb and deflect radiation. Space weather impact on satellites. Space weather can affect satellite operations and longevity, leading to costly repairs and replacements. Astronaut health. Long-duration space missions must account for the effects of space weather on astronaut health, both in terms of radiation exposure and psychological well-being. Radiation storms. These short-lived but intense bursts of radiation can pose immediate health risks to astronauts outside of Earth's protective atmosphere. Space weather monitoring. Organizations like NOAA and ESA operate dedicated space weather monitoring systems to provide real-time data and forecasts. Interplanetary magnetic field. This magnetic field, carried by the solar wind, plays a crucial role in shaping the space weather experienced in our solar system. Mars weather. The Martian atmosphere experiences dust storms and temperature variations which impact missions to the red planet. Asteroid impacts. Space weather also plays a role in asteroid dynamics and their potential collision courses with Earth. Spacecraft navigation. Accurate navigation in space relies on precise understanding of space weather and its effects on spacecraft. Solar proton events. These events can release high-energy protons that pose risks to astronauts in deep space. Galactic cosmic rays. These high-energy particles from outside our solar system can affect space missions and the health of astronauts. Solar sail technology. Space weather patterns, such as solar radiation pressure, can be harnessed for propulsion in solar sail technology. Space weather and astronomy. Space weather can impact observations from telescopes and observatories, affecting our understanding of the universe. Geomagnetic reversals. Earth's magnetic field has reversed its polarity several times in the geological past. During these events, the magnetic field weakens and can expose our planet to more space radiation. Mars dust storms. Mars experiences enormous dust storms that can engulf the entire planet. These storms can affect spacecraft on the Martian surface and even block sunlight from reaching solar panels. Heliosphere. The heliosphere is a vast region of space surrounding the Sun, shaped by solar wind and magnetic fields. Understanding its boundaries is critical for space weather modeling. Radiation belt variability. The intensity and behavior of radiation belts, such as the Van Allen belts, can vary significantly due to space weather conditions. Radiation shielding innovations. Ongoing research aims to develop more efficient radiation shielding materials and technologies to safeguard astronauts during long-duration space missions. Solar observatories. Space agencies worldwide operate solar observatories, such as the Solar and Heliospheric Observatory SOHO and the Solar Dynamics Observatory STO, to monitor the Sun and predict solar activity. Magnetic storm impact on technology. Magnetic storms caused by space weather can induce electrical currents in power lines, transformers, and pipelines on Earth, potentially causing damage. Communication challenges. Space weather can lead to radio signal disruptions and degradation of GPS accuracy, affecting navigation and communication worldwide. Astronomical instrumentation. Space weather can interfere with sensitive astronomical instruments like radio telescopes and interfere with observations of celestial phenomena. Space tourism risks. As space tourism becomes more accessible, understanding and predicting space weather becomes crucial for the safety of civilian space travelers. International collaboration. Space weather research and monitoring often involve international collaboration, as the effects of space weather are not limited by national boundaries. Microgravity effects. Space weather can indirectly impact astronauts' health by influencing the Earth's magnetic field, potentially affecting bone density and immune system function. Solar observing satellites. Space weather forecasts rely on a network of satellites, including those specifically designed to monitor the Sun and its activity. Space weather modeling. Advanced computer models are used to simulate and predict space weather events, providing valuable information for decision-makers in space operations and satellite management. Ionospheric scintillation. Space weather can lead to ionospheric scintillation, causing distortions in radio signals and impacting navigation systems like GPS. Space weather impact on financial markets. In our modern world, space weather can even influence financial markets, with disruptions to communication and power infrastructure affecting trading and economic stability. Lunar dust storms. The Moon also experiences dust storms, albeit on a smaller scale than Mars, which can affect lunar surface operations and equipment. Space weather education. Educational programs and initiatives aim to raise awareness about space weather and its impact on daily life and critical infrastructure. Mitigation strategies. Space agencies and organizations develop strategies to mitigate the impact of space weather on space missions, satellite systems, and Earth-based infrastructure. Future space weather forecasting, advancements in technology, and our understanding of space weather will lead to more accurate and timely forecasting, reducing the risks associated with space exploration and satellite operations. In the ever-expanding cosmos, the realm of extraterrestrial weather patterns provides us with profound insights into the complex dynamics of space. These intricate forces, driven by the sun, cosmic rays, and the magnetic tapestry of our solar system, have profound effects not only on our quest for understanding the universe, but on our daily lives, technology, and future endeavors in space exploration. As we navigate the boundless expanse of outer space, the ongoing study of space weather remains an imperative pursuit. With growing international collaboration and advances in space weather modeling, we are better equipped to forecast and prepare for the celestial tempests that occasionally visit our planet and the new frontiers we dare to explore. Space weather's impact on communication, navigation, astronaut safety, and even our understanding of the cosmos itself underscores its paramount importance. The quest to unravel the mysteries of space weather continues, as we strive to safeguard our technological infrastructure and the dreams of humanity's future among the stars. Thank you for joining us on this cosmic journey today. We hope you've enjoyed exploring the wonders of the universe with us. Before you go, make sure to subscribe to our channel and turn on notifications so you never miss another exciting space adventure. Just click that subscribe button and ring the bell. If you missed our last cosmic adventure, you could catch up right here pointing to the left. And get ready for our next space odyssey by clicking over here pointing to the right. Connect with us beyond YouTube by subscribing to Far and Beyond Earth channel for more in-depth articles and updates. Before we go, here's a thought-provoking question for you. What's most mesmerizing about Far and Beyond Earth? You'd like to learn more about? Share your thoughts in the comments below, and let's continue the conversation. Thank you once again for being a part of our space-loving community. Join us in our quest to explore within our world, into the cosmos, and together, let's reach far and beyond Earth. Until next time, keep looking up to the stars. Please help us by clicking like, subscribe, and share. For more videos, Far and Beyond Earth.